Okay, welcome to a very brief review of the summer materials. Most of these are memorization things, so probably the only thing we're going to really work on today are the Net-Ionic portion of this. I have a couple other places where we're going to do percent composition and empirical formula, but first item looked like solubility rules in polyatomic ions. There's just no way around it. You just have to memorize those. But this would be a helpful hint for you, is if you can kind of think about when you would actually have to worry about solubility rules and when you'd also have to worry about something being an ionic compound that can actually break up into ions. And so you have to have water present. If there's no water, you can't be worried about solubility rules. For the item to break up into ions, you have to have it be ionic. And then thirdly, you do have to know the solubility rules, which items that are ionic and water available would be able to dissolve in water. So if you know these four solubility rules, I think it's going to get you well on your way to knowing all of them. You can certainly memorize all of them. If you memorize these four, this is usually going to get you far enough. So these are all ones that are always soluble. So any of the alkali metals, no matter what they're with, as far as a nonmetal, would be soluble, like NaCl. Na is an alkali metal. Any nitrates, any ammoniums, and any acetates, no matter what they're with, would be soluble. So if you know which ones are soluble, then you might know then in the chemical reaction which item would be insoluble. Okay. I know that in the past, many students have trouble with when should we write an ion and when should we write a non-ion, a elemental. So copper is like a copper penny, like an old pre-1982 penny is mostly copper. And then copper ions, I have a picture of copper +2 ions are blue when they're dissolved in water. So very, 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 very different. Another example would be Na metal, sodium metal, is super reactive with water. You certainly wouldn't want to be ingesting any sodium metal, but people ingest sodium ions all the time, and that's just, like salty foods. And I think most people think that tastes pretty good. So I have a little description of what the differences would be of those two, and you can't get them mixed up because they are different. Okay, so this is the same thing that's in your summer materials or something very similar to this. This just gives you an introduction of how to write a Net-Ionic equation. And I think maybe when we first start out, we would start with writing out an entire full out chemical reaction. But very quickly, we're gonna just start writing beginning and finishing with just the simplified Net-Ionic equation. These are the only items in the chemical reaction that actually react. Everything else is along for the ride. They're called spectator ions, and they're not involved in the chemical reaction. And in this case, the sodium and the chlorides never participate in the chemical reaction. So I have two sodiums here, two sodium ions here, they cancel out. And I have two chloride ions here and two chloride ions here, and they cancel out. So what I'm left with is my Net-Ionic equation. Okay, so I think I'll do one of these for you in that format, like with 3 steps, but very quickly we're going to try to get rid of those 3 steps and go straight to the last step. And the way you are able to do that is knowing the solubility rules. So sodium ions, no matter what they're with, are going to be soluble. So that's how I got ions and ions. And then chlorides isn't one of those 4 rules, but I think most people know that the halogens, the halides, almost everything they're with, they're also always soluble. So that's how you can pretty quickly go straight to, again, that last Net-Ionic. But we'll practice this here. Okay. So this is how things would be presented to you, probably on a quiz or a test or the AP exam or whatever. So we have a solution. That means you have water available. We have silver nitrate. Silver nitrate, that's a metal ion and a non-metal ion. So that is a ionic compound. And also, generically, it's like AB. I don't know how you guys learned your chemical reactions, but most people learned them trying to figure out, is it a double replacement, single replacement, synthesis, so forth. So silver nitrate is reacted with magnesium metal. So we're going to call that just generically C. So it's like AB plus C. So you should be able to recognize that that's called a single replacement, and those two things are going to switch spots. Why those two things? Because it's a metal, is going to, C is the metal, that's the magnesium metal. It's going to replace the metal ion. So the C is going to go where the A was, and the A is going to go where the C was. So when you're done, you're going to have CB plus A. So the metal becomes an ion, and the ion becomes a metal. What didn't change is the, let's change a color here, is the B part. And the B part was the, in this case, nitrate. It was something nitrate to start with, and it was something nitrate to finish with. So nitrate is going to be a spectator ion, and we'll catch that. We'll figure out how that's going to be in a second here. So we have silver nitrate, and you have to be good with knowing what the charges are and what the polyatomic ions are. There's just no way around that. You're going to have to memorize that. And then magnesium metal is Mg. Now you will have a periodic table, so you'll be able to look at a few things. So I said that the metal and the metal ion, the cation, will change spots. So it'll be magnesium with nitrate. Now you have to know how to put these together. Mg is in the +2 column of the periodic table. So it's a +2 ion. And nitrates are a -1. So you're going to need 2 nitrates for every magnesium. And then silver metal, I said. Okay. So now we could balance that, I guess. Let's see, we would need 2 there and a 2 there. Now the second step, we'll break it into a different color here, should be breaking up any soluble ionic compounds, and since we have water available, you can do that. So we have 2Ag plus 2NO3 minus, the 2 carries through, magnesium metal makes magnesium. Remember, nitrates are always soluble no matter what they're with. And then that was metal. Metals and metal ions aren't the same thing. Cations and metals aren't the same thing. But what we do have, we can cancel some things out. Let's grab another color here. We could go, the nitrates could cancel. And I already told you that was going to happen. That was our B. Okay, so what's going to be left? Let's go back to our red. we're going to have the 2Ag plus the magnesium metal goes to magnesium ions and silver metal. And what should be done is double check yourself. Let's box this up here. This is a nice habit to get into for tests. Why? Because when you have a bunch of work, you want the teacher or the AP grader in May to be able to know what you want graded. Anything inside the box is going to get graded. If you don't box anything, you allow me to figure out what I want to grade. And I don't think you want me to try to figure that out. You want to tell me what to grade. Okay, so I have 2 AGs on the left. I have 2 AGs on the right. I have 1 mg on the left. I have 1 mg on the right. Now, I also want to make sure the charges balance. I have a 2 times a plus on the left, and I have a +2 on the right. A +2 is equal to a +2. So they're not going to be 0 equals 0. They're going to be whatever charges equal whatever charges, but you want those numbers to be the same. So that balances and we're good, and that is done correct. Okay, next one, solutions. What does solutions mean? That means you have water. Here, let's get rid of that. So let me erase that. Let's start over again. Whoops. Okay, so we have H2O because it has solutions. Calcium acetate is like AB, calcium acetate. Sodium carbonate is like CD. AB plus CD, you should recognize that that's called double replacement. In double replacement, you're going to get a precipitate. You could also get an acid base, but we're not ready for those yet. But we're going to get a precipitate. So some part of calcium acetate is going to be part of a precipitate. And some part of sodium carbonate is going to be a part of precipitate. Well, I know sodiums cannot be part of a precipitate because that is always soluble with whatever it's with. So that means it must be the carbonate. So we're going to go and start trying to transition straight to answers. So carbonate is CO3 minus 2. So what could carbonate mix with to make a precipitate? Could it make a precipitate with calcium ions or with acetate ions? You can't have 2 anions make a precipitate. You can't have 2 cations make a precipitate. You need a cation and an anion. So since carbonate is an anion, it must be the calcium part. Not calcium metal. It's calcium acetate. That means it's an ion. And that's the ion that is calcium because it's in the second column of the periodic table. So you combine those together and you get calcium carbonate. And it's already balanced. I'll do the little box routine here. Whoops, I actually can't do the box. I forgot to do that part of it. So that's not going to work. So let's go and do that now. Yeah, there we go. Okay, so what happened to the acetate and what happened to the sodium? Those are spectator ions. They were in solution before you started, before the reaction began, and they're still in solution. They're floating around the beaker when we're all done. So they weren't part of the reaction. And these are going to take some practice. Okay, ammonium phosphate, that's like AB, ammonium phosphate. And then solution, by the way, means you have water in the beaker. And then barium chloride is like CD. AB plus CD, that's a double replacement reaction. It's forming a precipitate. Oh, it already tells you it's going to form a precipitate. So sometimes it'll actually give you extra information. So what part of ammonium phosphate could form a precipitate? Well, ammonium is soluble with everything, so it can't be that. So that means it must be the phosphate. So let's put the phosphate in. So there's phosphate. So phosphate is an anion. So can anions and anions come together and make a precipitate? No. That's how I know it's got to be barium. And barium is in the second column of the periodic table. So it forms that way. And it doesn't matter if you put the cation first or the anion first. I would say it looks a little more professional if you put the cation first and the anion second, but the way I put it here, that's perfectly fine and you get full credit. So, but what is important is how you combine these. The cation has to go first in the precipitate on the right-hand side. So here's barium and here's phosphate. But remember that every time you combine a anion and a cation, they have to combine in the right ratios. So I use the drop-down method. I teach that in my first-year chem class. And that is taking barium's ion charge +2 and dropping it down to phosphate. And then I take phosphate's charge, which was a -3, and bring that down to barium. And if you do that, that's going to work out. The only time it wouldn't work out for you is if it was something you could divide by. Like if it was a 2 and a 4, you could divide both those by 2. So you could go to a lower common denominator, a lower ratio. So now we have to balance it though. 3 bariums on the right, so we need 3 bariums on the left. 2 phosphates on the right, so we need 2 phosphates on the left. And then lastly, we should look at the charges. On the right side, that compound has no charge. So that means we should have no charge on the right. We have a 2 times -3, that's -6. And we have a 3 times +2, that's a +6. A +6 and a -6 equals 0. So that works out. So let's box that up and move on. And it's definitely going to take a little bit of practice for you guys to get to that that quickness, I guess. But it starts off slow, but you guys in very quick order will be really good at these. You just have to practice. Okay, chlorine gas. That's like, we'll call that A. Bubbled into a solution. Again, solution means you have water available. And sodium bromide. Sodium bromide, we'll call that BC. You could call it whatever letters you want. I'm just starting at the beginning of the alphabet. So A plus BC. That's a single replacement. That means the A has to replace the part that it's able to replace in BC. So chlorine gas is a nonmetal. So it's going to replace the nonmetal part. I think I might write this one entirely out. So chlorine gas is not Cl. You do have to know there are the Brinkelhoffs. And if you ever see it, chlorine, bromine, iodine, oxygen, hydrogen, nitrogen. I might have forgotten one or two there. Fluorine. They are always diatomic molecules in their elemental state. So we got Cl2, and then we have sodium bromide, NaBr. Okay, let's change this color here. So these two things are going to switch spots. The chlorine's going to go where the bromine is, and the bromine's going to go with the chlorine. But every time you form an ionic compound, you have to make sure you do the right combination of ions to make that a neutral charged ionic compound. Okay, let's go back to our red. So the bromine's going to be by itself, but it's also a Brinkelhoff. It's a diatomic molecule in its elemental state. And then the Cl is going to go where the Br was. And both those are +1 charge and a -1 charge, so you need one of each of those. Very often, kids like to try to put a 2 there because there's a 2 over on the left. Nope, that's not the case. You have to make sure you build these molecules each and every time with the charges that they already have. Na has a +1, Cl has a -1, so you need one of each of those. But we are able to balance it. So 2 chlorines on the left, so that would give us 2 chlorines on the right. But now we screwed up the sodiums. We have 2 sodiums on the right, so we need 2 sodiums on the left, and we actually already have now balanced the bromines. That would be a good reaction, but that's not a net ionic. So net ionics, we have to be able to break everything up into ions if it's able to be broken up into ions. That's not ionic, that's covalent. So we're going to leave that as is. This is an ionic compound that's soluble in water. So that gets broken up. And remember, we had water available because it said solution. And remember, I was telling you that I would like you guys to get away from that step that I just did as soon as possible. I'm just showing you this so we don't lose anybody. And then I'm going to cancel out anything that I see that's exactly the same on both sides. And that is the same on both sides. So now we can go and finish it up. And why again do people write Net-Ionics? It's to show just the materials, the species that are actually being reacted in the chemical reaction. So if you look at the charges, charges will balance on both sides. So you have -2 charges on both sides. And all the atoms balance on both sides. So that satisfies the law of conservation of mass. Okay, that might have been it, maybe. Yeah, it was. Okay, so that gets you a start. I would recommend going back and redoing a few of those. You can always find more on, you could go just Google Net-Ionics, and that should get you pretty much started with what we need. So that'll be it.